Hi everyone, this is Yanni. I'm a software engineer from Meta AI. Today I'm presenting for our paper PyTorch FSDP, Experience on Scaling Fully Sharded Data Parallel. I'll first give an introduction and overview of PyTorch FSDP API, and then deep dive into its design. After that, I will share our experiment evaluation results. PyTorch FSDP API is motivated by the trend of rapidly increased model sizes in AI area in the past few years. The API is designed to be generic and user-friendly. It is an industry-grade production-ready solution for large model training. It is exciting to see its successful launch and wide adoption so far by open source communities like AWS, IBM, Mosaic ML, Mobileye, and more. Let's look at its algorithms overview. Overall, the FSDP algorithm shards parameters, gradients, optimizer states, and activation. So it's called fully sharded. FSDP breaks down a model instance into smaller units and then flatten and shard all of the parameters within each unit. The sharded parameters are communicated and recovered on demand before computations, and then they are immediately discarded afterwards. This approach ensures that FSDP only needs to materialize parameters from one unit of parameters at a time, which significantly reduces peak memory consumption. Let's deep dive into its design. The first one is a large model initialization. PyTorch traditionally requires the full materialization of the entire model instance on one device or host memory. It's very challenging to initialize a model that cannot fit in the device or even CPU memory. We introduced the deferred initialization method. It combined with FSDP. The deferred initialization context manager first initialize a model on fake device and then pass the model to FSDP. FSDP will initialize and shard one unit of parameters at a time to device directly. This design makes large model initialization very easy as it does not require users to modify the model authoring code. It is also very fast because all the initialization and sharding happen on the device directly. FSDP offers a variety of sharding strategies, and they are configurable, ranging from fully replicated to fully sharded. Assume sharding factor F is the number of ranks over which parameters are sharded. When F is equal to 1, FSDP fully replicates the model and simplifies to vanilla data parallel and use or reduce for gradient reduction. When F is equal to the word size W, FSDP will fully shard the model and each device only holds 1 divided by W of the model. Hybrid sharding occurs when the sharding factor is between 1 and 2 W. For example, above this figure showed the model is sharded over 8 ranks and each shard is replicated. 8 ranks and each shard is replicated. Configurable sharding strategy provide flexibility for users to make trade-off between memory saving and communication overhead. FSDP also incorporates a range of native communication optimizations. Communication and computation are overlapped by leveraging multiple device strings and asynchronous operations on device. Backward prefetching and forward prefetching are designed to further improve communication and computation overlapping. The prefetching is based on the recorded execution order. Okay, the last one is the rate limiter design. PyTorch uses a CUDA caching allocator as a middle layer to serve GPU allocation and free requests for PyTorch programs. In order to efficiently manage memory, FSDP uses a rate limiter to take into account the memory impact of the caching allocator on programs that use several CUDA strings and run fast CPU threads. When CPU thread is fast, over-prefetching all gathers could easily result in out of memory. Rate limiter throttles the prefetching pace and keep the system memory in a healthy state. We conducted evaluation for different sizes of language models and recommendation models on 1 to 512 A100 80 giga GPUs that are connected by a 2 TB per second Rocky network. The objective of experiment was to assess the capability, efficiency, and the scalability of FSDP in training large models. We've evaluated Hugging Face T5 series models. The performance of FSDP and DDP is similar when evaluating small models. However, DDP encounters an out-of-memory error when attempting to run models larger than 2 billion. In contrast, FSDP can easily accommodate the 11 billion model and achieve significantly higher TFLOPs by turning on bfloat 16. These experiments illustrate that users can utilize FSDP for both small and large models, just by smoothly configure the sharding strategies. With the mini GPT 175 billion model, the experiments achieved more than 180 TFLOPs per GPU with batch size 2. This is equivalent to 60% of GPU hardware utilization. Furthermore, the model demonstrated linear scalability from 128 GPUs to 512 GPUs, which affirms the efficiency of FSDP in handling large models on high-speed network interconnections. For the large recommendation model, the large sparse tensors are sharded using a dedicated sparse sharder, while dense modules are sharded using FSDP. Experiments results showed FSDP can efficiently accommodate the large DHEN recommendation model. In particular, the hybrid sharding showed better performance when running on the large number of GPUs, 512 GPUs here. Okay, this is the final part. Let's recap summary here. We demonstrated FSDP attains usability and efficiency through a set of advanced techniques. All of these techniques are closely co-designed with other key PyTorch components to ensure the solution is sound and robust. FSDP can facilitate large language and recommendation models with linear scalability. Finally, we want to thank the PyTorch community and the PyTorch FSDP users for their feedback and contributions.